This is 4.5 part 2. We're going to continue factoring some difference of squares. We did examples 1 and 2 already. Let's move on to examples 3 and 4. So once again, we identify if we have a special case of difference of squares, and it looks like in this case we do. The first term is a perfect square, meaning you can take its square root and you get a nice whole number and a variable that works out as well. So square root of x of 9x squared is 3x squared. And then you can also take the square root of 36, and that gives you a nice whole number as well, which is 6. So 36 is a perfect square, and they're connected by a minus, which means we have a difference of squares, so we could use our technique that looks like this. So we have two brackets, find the square root of the first term, so square root of 9x squared is, oops, I shouldn't say 3x squared, I should say 3x to the power of 1, which is just 3x. So put 3x in both. And then square root of the second term, which is 6, so we have 6 here. And then we put plus in one of the brackets and minus in the other. And if you had put minus in the first and plus in the other, it doesn't matter. You can write these in any order. It's kind of like saying 2 times 3 is the same as 3 times 2. It doesn't matter the order when it comes to the multiplication, so you're fine if you did that either way. So if I put the minus here, the plus there, it doesn't matter. But I'm not fully done yet. I want to make sure this is fully factored. So what I do is I can take out a common factor from these brackets. So I can take out a 3 from this one. So I'd have something like this, 3 taken out of there. If I take 3 out, I'm just dividing every term in there by 3. So this would be x plus 2. And then I could also take 3 out of this one. So there's another 3 there. And then I could have 3x. Oops, I divide by 3, so that would be, let me erase that. I could have x minus 2, because minus 6 divided by 3 is minus 2. And then I can simplify. I can simply multiply my 3 and my 3 here together, and so that would give me 9 bracket x plus 2 bracket x minus 2. And so we did the difference of squares method, and then we took out the greatest common factor from each of these separate brackets. You could have alternatively taken out the greatest common factor first. So you could have done greatest common factor looks like it's 9. So you would have had 9 brackets. 9x squared divided by 9 is x squared. And then minus 36 divided by 9 is minus 4. And then you would have had a nice easy difference of squares to solve over here. You would have noticed that your first term is a perfect square. If you do the square root of your first term, square root of x squared would give you x. So you could write x over here and x over here. And your last term is a perfect square as well. Square root of 4 is 2, so you would put 2 and 2 here. And then put your plus here and your minus here. And you would have had the same answer. So it really depends on your preference. I often like to take out a greatest common factor first because it makes my difference of squares inside the brackets a little bit easier to follow. Just make sure that you don't forget to put that coefficient, that 9 there in the front every time, or that multiplication of 9 in the front every time. Some students continue their work and they forget to put that 9 there, and so now they have something that's worth 9 times less. So let's go on to example 4. Let's take a look if this is a difference of squares. So it is, and the reason I know it is because again I have x to the power of 4. And you can do square root of x to the power of 4. And square root of x to the power of 4 is going to be x to the power of 2. So that is a perfect square there. And so I'm going to make my set of brackets here. Let's just double check, see if 16 is a perfect square. It is. Square root of 16 is 4. So I will have x squared. So be careful there. If you have x to the power of 4, when you square root that, it's x squared and x squared, not x and x. Otherwise, when you re-expand, you will not get x4 again. And then we have our square root of 16 is 4. So we have plus and minus. And so what you'll notice is you kind of factor this, but you can factor this a little bit more. If you look at this one over here, you'll notice this is another difference of squares. You have perfect square for x squared, perfect square for 4. So you could further factor this and have a nice fully factored expression. So this would become x bracket x. The square root of x squared is x. Square root of 4 is 2, so plus 2 minus 2. Don't get caught off guard here. This x squared plus 4 here, that's not a difference of squares anymore. Well, why? Well, it's not a difference. So even though x squared and 4 are perfect squares, this is not a difference, so that you cannot factor anymore. You can try all you want. When you see something like that, where you have x squared plus something, you will not be able to factor that anymore, so you leave it as is. So we have x plus 2, x minus 2, x squared plus 4, and that will give us our fully factored form. So if you have something other than x to the power of 2, when you take its square root, you need to be careful to account that you're not just going to have x and x there. You might have x2 and x2 there. If this was an x3, for example, that's no longer considered a perfect square anymore. You need to be careful with that. When you do the square root, some students get confused here. How did I know the square root of x4 is x squared? Well, whenever you do square root, what you're doing is you're really taking this value here, x to the power of 4, and square root really means you're putting that to the power of 1/2. So basically you're multiplying the exponent on the inside here by half. 4 times half is x squared. It's no different from what we did over here or over here. What you're doing is, let's just do the square root of x squared there. You're really just saying x squared to the power of half. So you're multiplying the exponent 2 by half, which is 2 times half is 1. So that gives you x. If you had x cubed and you tried its square root, you would be doing x cubed to the power of half. And that would give you x to the power of 1.5. So that would not be considered a perfect square. So be careful with that. Make sure it's something that you can square to get nice whole numbers, no decimals there, to get your perfect squares, and then see that you have both terms of perfect squares, the first one and the second one here, and then make sure there's a minus there so you can actually do the difference of squares method. So we'll do a few more examples together to make sure we have the hang of it. We'll do some examples where there are 2 variables this time. It's very, very similar. You just have to make sure not to forget to write the second variable. This example we already did together, but you can retry it yourself and then verify it by expanding. Let's try this example here. So first of all, let's see if it's a difference of squares. Can we do square root of 9x squared and get nice whole numbers that that are multiplied by each other? Well, let's take a look. Square root of 9x squared is basically just square root of 9, which is 3, and square root of x squared, which is x. So perfect. That's a perfect square. Square root of 49y squared. Well, square root of 49y squared is basically just square root of 49, which is 7. Good. And then square root of y squared, which is y. Good. That's a perfect square. And there's a minus in between, so that means we have a difference of squares here. Since we have a difference of squares, we can proceed to do our difference of squares method of factoring. So we can write our brackets, take the square root of the first term, we said it was 3x, put it in both brackets. Take the square root of the second term, we said it was 7y. Don't forget, you can't lose that y. 7y, 7y. And then just put a plus and a minus. Take a look to see if you can factor anything out from the individual brackets to put in the front. It doesn't look like it. You can't take a 3 out because there's a 7 there. You can't take a 3 out because there's a 7 there. So in this case, it looks like we're fully factored with an example like this over here. So that's an example where you have 2 variables this time. Make sure you don't forget that second variable. Let's try example C here. Let's see if we have a perfect square. At first glance, it doesn't really look like it. It looks like because you can't do square root of 8 and get a nice whole number, and you can't do square root of 50 and get a whole number. So what I recommend you do in this situation is, again, take a greatest common factor out. A greatest common factor. And it looks like a good common factor that we can take out is 2. If you take out a 2 from this, you get 2 times 4x squared minus 25y squared. And so now you'll notice what's inside the bracket can actually be a difference of squares. We have a perfect square for 4x squared and a perfect square for 25y squared, and there's a minus there. So we can continue by breaking that bracket up into 2 brackets, taking the square root of the first term, which is 4x squared, and so that gives us 2x, because square root of 4 is 2, and square root of x squared is x, so 2x. Put that in both brackets. Take the square root of the second term, square root of 25. Don't forget the y squared there, because there's 2 variables. And we get 5, because square root of 25 is 5, and then y, because square root of y squared is y. So we write that in both brackets, 5y, 5y, and then put your plus and your minus. And take a look if you can factor anything else out. It doesn't look like it, so here we have a fully factored form of this over here. So the greatest caution I can tell you is to make sure that you, before you jump to conclusion and say you don't have a difference of squares, take out that greatest common factor. Try to take out a greatest common factor whenever you can, so that way it creates a simpler bracket to factor later on. Either way, you'll have to take out a common factor near the end anyways to have full marks, to be as simplified as possible and factored as possible. So we just did some examples of difference of squares factoring. You know how to identify difference of squares and how to factor those. We're going to take a look at a second special case called perfect square trinomials. We're going to start off defining them in this video and seeing how we can identify them, and then we're going to do some examples of how we can actually factor them using a cool technique. So if the factored form of a trinomial looks like this, a plus b squared, or a minus b squared, the whole thing squared, not just b squared, the whole thing squared. These are called perfect squares, and their expanded forms would be called perfect square trinomials. Perfect square trinomials. So an expanded form of this would be, if you were to just write this out as a plus b multiplied by a plus b, you would get a squared plus 2ab plus b squared. Whereas if you had this one here, its expanded form would be a minus b times a minus b. So I'm just showing you we're doing FOIL here. If you do FOIL and expand fully, you would get similar idea, a squared. Instead of plus 2ab, you'd have minus 2ab. And you would have plus b squared. So the main difference is that middle term in this case. So if you have a plus b all squared or a minus b all squared, we call this a perfect square factored form. And when you expand it, its expanded form is called a perfect square trinomial. And so you know you have a perfect square trinomial if the first term that you're dealing with is a perfect square. Perfect square. Okay. If the third term, so this is our first term, third term is also a perfect square. And the middle term, there's two possibilities, okay? The middle term will be the square root of the first term times the square root of the last term times 2 if it's positive, or times negative 2 if it's negative, as you can see here and here.